you guys, another video here for Rawls' theorem. And the MBT. Okay, so for first semester, you're going to have your existence theorems are going to be IVT, EVT, which is also the candidates test, and then Rawls and MBT. Okay, and then you only learn one of these existence theorems in semester 2. Okay, if a function is continuous but not differentiable at x equal to a, then we have a corner, a cusp, or a vertical tangent at x equal to a, okay? So, that's just a little review statement. Sketch a function that is continuous on the closed interval ab, differentiable on the open ab, and where we have two y values that are the same. So list two different possibilities. Well, we could do okay, so there's a closed interval AB and differentiable, so we don't want any corners or cusps or vertical tangents, so like smooth curves, and we want it to be continuous with smooth curves. So I could do that. I could do that. Hit it. All right, I could do that, or I could do multiple places. Okay, so if I was going to draw in a secant line through the inputs of the graph, it would look like that. It would look like that. That would be the graph itself, and that. Okay, so the secant line is horizontal. So the slope of the secant line is 0. All right, if we draw a tangent line parallel to the secant line, the two lines will have the same slope. Okay, so this is secant, 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 secant. All right, so now let's do the tangent. 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 And I'm making the tangent parallel be the same. Even do one parallel down here. So tangent. 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 And tangent. All right, so here is the theorem. The theorem is the slope of the tangent line at xc at this some c value is equal to 0. The tangent line x equal to c for some c value is 0. So conclusion, there exists at least one c in AB such that f prime of c is equal to 0. In other words, there exists at least one parallel, which in this case is horizontal. Okay, and that's Rawls' theorem. Our hypothesis is continuous on the closed interval, and it has to be differentiable on the open. Interval is AB. So if you have two y values that are on level, okay, there's your if, and all of this is part of the if too, then there is at least one number c. So this would be right here c. This would be right here c. This would be anywhere, and then this would be, you'd have three of them here. 1, 2, 3. So you have c, c1, c2. Okay, such that f prime of c equals 0. This is only an existence theorem. It does not tell you the value of c. All right, So let's do a little problem here, and then I think I'll pause because the bell's going to ring. We'll have some shuffling. Okay, so this is continuous. Sorry, got this mixed up. F is continuous because it's a polynomial. All right, and this is the closed interval. All right, I'm going to pause this shuffling. I'll be back in about 3 minutes. Okay, class is out, so here we go. Let's finish this. Let's see. Find all the values of C such that we get a derivative equal to 0. And so it's a polynomial, so it's continuous and differentiable. On negative 2, 2. All right, so if you look at the endpoints, f of negative 2, okay, if you plug in f of negative 2, you're going to get 16 minus 2 times 4, all right, so you're going to get 8. And if you plug in f of 2, you're going to get 16 minus 2 times 4, which is also 8. Okay, so since this equals 8 and this equals 8, they're on level. You've got the fact that f of negative 2 equals f of 2. By Rawls' theorem, there exists a C and a B such that the first derivative is 0. So then it says to find. It does not guarantee. It guarantees that it's there, but it doesn't find it. So really, we just have to take the first derivative and set it to 0 to find C right here. First derivative is 4x cubed minus 4x, okay? And we're simply going to factor out of 4x, set it to 0, factor out of 4x, x squared minus 1, and so x plus 1, x minus 1, x equal to 0, negative 1, and 1, all right? It looks like there are 3 of these where you will see this happen. Okay, so let's find the y values, I guess, for those. This will be 0, 0, it'll happen. There will be a horizontal tangent. If I put negative 1 in here, I'll get 1 minus 2, so negative 3. And if I put 1 in here, I'll get 1 minus 2. So negative 2. I can't seem to do my math today. Negative 1 goes in there, and that's positive 1 minus 2, which is negative 1. All right, so there's that, there's that, there's that. So I know this has got to be a tangent, right? Have that horizontal tangent. And then also here, from the behavior of this graph, this will go up, up. So we pretty much know what this graph looks like. All right. We could have done our x-intercepts here also, but I think this is enough for us. So Rawls was telling us there's some point, there's actually 3 here, where the first derivative equals 0. Okay, next page. Mean value theorem, next page. Get out of here on time. All right, so this is kind of like Rawls, except we're just not looking at 0. Okay, we're looking at just some random slope. So this basically, long story short, says if we're continuous on the closed and differentiable on the open, and if we have these not equal. All right. So there's some point, so this is going to be a f of a. This is just Rawls' theorem with a slant. So if we're continuous and differentiable, so nice smooth curve, continuous, and we have these endpoints. If I draw a secant line, there is somewhere where, pre-algebra slope secant will equal calculus. There's at least one C value, that would be right here, where the tangent line equals the secant line, okay? So draw the secant line, we did that. The slope of the secant line is f of b minus f of a, b minus a. The tangent line parallel, that would be, f prime of c. Since the tangent line at x equal to c is parallel to the secant line, through the endpoints, the slopes are the same. Therefore, f of prime of c is equaling this f of b minus f of a, b minus a. So it's basically calculus meets pre-algebra at one particular point, as long as it's continuous and differentiable. Okay. So this says there exists a tangent line at an interior point parallel to the secant line through the endpoints. The slope of the tangent line, the interior point, equals the slope of the secant line through the endpoints. Okay, and that's average rate of change. We could extend this to the instantaneous rate of change at an interior point is equals the average rate of change over the total, the whole interval, the closed interval, or through the endpoints. Average rate of change through the endpoints or of the endpoints. All right, so let's formalize it and we will call it a day. If we are continuous on the closed and differentiable, I keep doing that, differentiable on the open, then there exists at least one point where the first derivative meets good old-fashioned pre-algebra slope. Okay, so there's that. I mean, you could play with this if you want. If you wanted to solve for f of b for some reason or not, you could always say f prime of c times, if you were just doing your algebra here, times b minus a plus f of a. So, you can always manipulate this if you need it in a problem. Okay. The MVT ties together the average rate of change and the instantaneous. Okay. Okay. Rates of change. And this, again, is only an existence theorem. It does not tell you the value of c, but all you have to do is set it equal to that slope value. All right, so let's check it out. First of all, f of x is continuous on -1, 1, and diff on -1, 1 open, because polynomial. It's a polynomial. I'm running out of room here. So there is at least one value such that f of c equals this slope. All right, so we're going to put in 1 minus 1, 1 minus -1. F of 1 minus f of -1, 1 minus 1. All right, so let's figure out what that is. Good old-fashioned slope. One plus 1. Okay, so this is going to equal 2, and f of 1 here will just be, let's just do f of 1 here. That'll be 1 minus 1 minus 2, so that's minus 2. And f of -1 is going to be -1 minus 1 plus 2. Okay? So that's going to be 0, but that's not right. So where's my arithmetic error? Let me pause and find it. Okay, so never mind, there is no error. This is 0. Okay, so that's negative 2 minus 0 over 2. So negative 2 over 2, which is negative 1. Okay, so there is somewhere where the first derivative is equal to a slope of negative 1. Okay? And so if we were to find it, we would take the first derivative, 3x squared minus 2x minus 2. Somewhere this is equal to negative 1. Let's find that c value. And let's let x equal c. Let's do that over here too. Okay, supposed to find the c value. Kind of a technicality, but okay. All right. So good old algebra 2 here, and that's going to be plus, here we go, that's factor. Okay, so check it, looks good. So we're looking at x equal to negative 1 over 3, or x equal to 1. This is an endpoint, so that's not going to work. So it's at x equal to negative 1 over 3 is where this is going to happen. So find the c values right there. All right, I don't know if I got the, oh yeah, I got the y value. So if you were to plug the y value in here into the original, if I did f of negative 1 over 3, that comes out to be, I just have it in my notes here, 0.519. Okay, so it says to do a graph here. If we were to graph that negative 1, we were at 0, and at 1 we were at negative 2. Okay, and so this graph is going through 0, 0 here. It's going to just do something, in which I would show you it's just doing something like this. Okay, and so here's the secant. Right, and then this is the tangent, the parallel tangent. And this c value here is where it's happening, and that c value point then is right here. That point is negative 1/3, 0.519, right here. Okay. So we're paced to go to the next page here, but I've been throwing this part out for years because it's a really super common sense question made incredibly difficult through calculus, and it just confuses everybody. So we're throwing that out. We will not need it on the test, anything like that. It's just kind of, it's just kind of, I don't like it, so we're not doing it. Okay, that's it for me. I'll see you guys when I get back from Santa Barbara. Thanks for watching. Bye.